Hi people, good morning. I mean, I'd say it's good evening. Let's see, six of you. We'll wait for 1 or 2 more minutes. So you can join and then start. Yeah, I think I can start now. Let me share my screen. Right. So today I'll not be switching on my video because I'm not feeling good. I took vaccine and stuff. Right. So yeah, the video will not be on for today. Maybe for next class, the video will be on. Right. Okay, so we have successfully completed your first chapter, that is some basic concepts of chemistry. We actually saw certain extra things also like titrations and stuff. Right. So today we'll start with the second chapter, and I told you this is going to be one of the most interesting chapters. Right. So that would be atomic structure. Right. So I already mentioned what all you're going to study. Right. I gave a quick introduction about this chapter last class, if you can remember. Right. I told you that you're going to start with not Dalton exactly, but yeah, you'll just touch Dalton. Then you'll want to see what are the discoveries like electron, proton, neutron, nucleus, and all that. And then you'll go for Bohr's. In between, you'll have J.J. Thomson, Rutherford, and then at last you'll go for quantum mechanical model. Right. So this is the roadmap of this chapter. Right. Okay. So we'll start. So we already know what Dalton said. Right. So Dalton, this was in 1800s. Okay. This was, I would say, even in 1700s. Okay. So Dalton, you know what Mal Dalton told? All matter is made up of atoms. Atoms are the building block of matter. Atoms are indivisible. Right. All these things he told. Right. Say if I have to just this thing. First one is it is indivisible. Right. And then if I'm going to say if I'm going to have one element, right? Say for example, sodium element, right? Sodium element will be made only of sodium atom, right? So that also he said in a particular element, only that type of atom will be there. In sodium element, you will not have chlorine atom. Like that's what I'm telling, right? That's the second point. Third point, right? He said that each atom has its own mass, right? Each atom will have its own mass. Right? That's what it's not atomic mass, guys. Like atomic mass, we know what is it? It is relative weight, right? Okay, so he said that each atom has its own weight, right? All these are simple points Dalton told. Okay, now we know what are all the problems we have here, correct? Obviously, atoms are not indivisible, right? Because we know now that atoms inside atoms, I have electrons, protons, nucleus, neutrons, everything is present, right? That obviously is not a correct statement. Atoms are divisible. Excuse me. Right? Okay. And the next point is this one, right? Each atom, I would say, in the correct way of putting it would be each atom has its own constant mass. Okay. Now, yeah, it is true for most of the extent, but when you look at isotopes, right? We know what isotopes, right? Can someone tell me what are isotopes?
Sir, same mass number but different atomic mass.
Same atomic number but different mass number. Okay, they will have same atomic number but different mass number. Basically, hydrogen, if I take hydrogen, has three isotopes, like hydrogen 1, hydrogen sorry, this is 1, okay, and hydrogen 2 and hydrogen 3, right? You see all of them are having atomic number of 1, right? But there's a mass number of 2, mass number of 1, mass number of 2, and mass number of 3, right? So same mass, I mean same atomic number but different mass number is what I'm going to have, right? Okay, now if I have same, also anyways, we'll not go into the details of this. So what I'm trying to say is that not all elements atom will have constant mass. Is it not? Say if at all I'm going to have any isotopes present like this for hydrogen or for bromine or for sulfur, so many isotopes are present. Okay, now that means what? That means they are not going to have any constant mass. We actually know how are we going to calculate this. Hope you remember. The atomic mass is equal to percentage abundance into the mass number plus per second percentage abundance into the mass number of the second isotope divided by 100. Hope you remember this formula. We saw it in the previous chapter, right? Atomic mass, if at all I have two isotopes and they have two different percentage abundances, right? M1 and M2, say for example, can be 1 and 2 for in the case of hydrogen, right? Say percentage abundance, say this is 97%, this is say 20%. I'm just giving you random numbers. So all this value you'll put here, and then you will be getting the atomic mass value, right? That means what? It is not a constant value. That's all you have to understand from this. Okay, fine. So because of all these problems, right? Atoms are divisible, right? Atoms are divisible. Now we know. We'll actually see how it all turned out, right? So the first person to disprove Dalton, okay, the first person to disprove Dalton was this guy, J.J. Thomson, right? So till then, right, till J.J. Thomson gave his theory, conducted his experiment, right, people were thinking that atoms are indivisible. There's nothing inside atom. They're very small, right? You will not be able to see them with naked eyes, nor with the help of a microscope. Even if you have a very powerful microscope, right, you will not be able to see atoms. Are not impossible. They're very small. Right. Anyways, so J. Thomson conducted this experiment, right? And then you know, like, or we already know from your lower classes, he was the one who discovered electrons. Right? He was the one who discovered electrons. Okay. Now we'll see how he did it. Right? How J. Thomson, right, with the help of what? He did some experiment. I think you also know the cathode ray experiment, right? So with the help of the cathode ray experiment, we'll try to understand how these electrons were discovered, how electrons came into the picture. Okay, fine. So for that, we have to look into this cathode ray experiment. Okay, right? So I'm going to draw a figure. Bear with me, please, because I'm not that good at drawing, right? Okay, so this was a setup. Okay, so he had a glass tube like this. Okay, this is made out of glass. Okay, now inside this, he put two conductors. I would say these are metallic conductors, or you can even call them as electrodes. Has anybody came across this term, electrodes? This term, ELEC.
Yes, sir.
Okay, so anybody, basically electrode is a metallic conductor. Nothing. That's what you have to understand. It's a piece of metal. Right? It can be iron rod, it can be copper rod, gold. It can be anything. Anything which is a good conductor. Okay, right. So those two electrodes you fit here, and then obviously through this you are going to give power supply. Very huge power supply, not Chuma power supply. Okay, almost like 10 to 12 volts you will give. Okay, we don't have to go into the numbers, but all you have to understand is it's a high power supply. Okay, right. Now, other than that, I had two openings in the glass tube. That is, say, one opening here. There is opening here, guys. Okay, and there is another opening here. Okay, right, fine. Now, through the first one, right, I will put vacuum pump. Very important. Right now, please understand, people, this particular experiment, right, whatever experiment we are going to conduct, or whatever experiment J.J. Thomson conducted, was conducted under partial vacuum. You have to understand this. We know what is vacuum, right? Vacuum means nothing is there. No, there is not, literally nothing. That is what is called as vacuum. So this vacuum pump, what is it going to do is it is going to suck all the extra air which is there inside. Okay, there will be obviously some amount of air or any other gases present. All these things is going to be sucked out with the help of this vacuum pump. Okay, now you can ask me, sir, why vacuum pump? Why we have to maintain partial vacuum? So if I have to answer the question, when he conducted this experiment, when J. Thomson conducted the experiment without vacuum, right? If it is like normal conditions, he was not able to see the results what he wanted to see. Okay, hope you understand. If he actually started the experiment with not vacuum only. He started the experiment with normal conditions. But what he wanted to see, that was not coming out properly. That means what? Obviously, for whatever has to happen, partial vacuum is a must condition. That's what you need to understand. Okay, fine. So the first opening is vacuum pump. Second opening is where I am going to put H2 gas inside. Okay, H2 gas inside. H2 gas, or even sometimes he even used helium gas. Okay, H2 gas or helium gas. Okay, right. So this is the overall setup. I still have, this one thing missing. I'll tell you what is that. Okay, so now people, actually, I have to put it ulta. Just give me a moment. I'll just change the circuit a little bit. I will put negative. This is negative, and I have to put a positive. Okay, fine. This is just for the convenience. I just changed the sides. Okay, so we know the smaller one is negative terminal, and the bigger line is the positive terminal. I think we all know that, right? This is negative terminal. I would say this is connected to the negative part. This is negative, and this particular thing is positive. Okay, and we know generally these electrodes we have here, right? These electrodes which we have here, right? Whenever that electrode is connected to the negative terminal of the battery, say I have some electrode, right? If I have only the electrode, we cannot call them as whatever I'm going to call. But if at all you see one of them is connected to the negative terminal and the other one is connected to the positive terminal of the battery, right? Now at those times, we will call them as cathode and anode. This one is anode. Okay, right? So negative terminal, wherever it is connected, it's called cathode. Positive terminal, whichever is connected, is called anode. Okay, this we have to understand. And one more important thing is that I am going to use perforated anode in this case, right? What I'm going to use? I'm going to use perforated anode. Okay, now what do you mean by perforated? Perforated means it is having holes in it. Okay, so this particular thing which we have here, right? This anode has, okay, I'll use some other color, maybe this has holes in it. Okay, this has holes in it, and after the anode, you still see some gap, correct? In the between the glass tube, this is the glass tube, right? And this is the anode. Between these two, you still have some gap. Okay, so what he did is that he gave a coating like this part, right? This part of the glass tube was coated with zinc sulfide. Okay, this part, I mean the anode end of the glass tube, right, is coated with ZNS, zinc sulfide. Okay, now I'll just repeat whatever is the construction here. There is going to be a glass tube, right? And inside the glass tube, I'm going to have two electrodes, one connected to the negative terminal of the battery, cathode, another connected to the positive terminal of the battery, anode, right? And then I'm going to have two openings in the tube. One is for maintaining vacuum, partial vacuum. I'm going to have a vacuum pump. And second thing is that I'm going to have an opening for H2 gas to come inside. Okay, right? And then when I come to anode, cathode is okay, no issues. When I go to anode, I am going to use perforated anode. Perforated means it is going to have some holes. Okay, and this end of the glass tube is coated with ZNS screen. Okay, that's it. This is the overall construction of the cathode ray or this experiment. For this experiment, this is the overall setup. Okay, now we'll see what is the working. What happens, right? What happens when I turn on the battery? Okay, I have the battery here, it will be switched off till now, right? Now I'm going to switch on the battery. Okay, I told you that it is a very, very high power supply, and then I'm going to maintain partial vacuum. All that is going to happen. Okay, fine.
Sir?
Yeah, please tell me.
Sir, before conducting this experiment, electrons were not discovered, right?
Correct, electrons were not discovered. I'm going to prove it to you through this experiment.
Sorry, sir. So how could he? How were there batteries, and how was there a circuit of an electric?
Oh, no. Yeah, that's a good question actually. So this power supply thing, no, like now we have the concept of electric current saying that it is the movement of electron. But if you went to history, 1700s, 1800s, right? They had an entirely different theory, right? They just saw current as a form of energy flowing. That's it, right? Like they got inspired from lightning, right? Even though you don't understand the mechanism between lightning, so what you understand is a different form of energy itself, right? If you can remember, I forgot that guy's name. Very famous for this lightning rods. Who's that? Franklin, something, right? Anyways, so that guy was the first inspiration. Then Tesla came, right? So like all these things, whatever I'm telling you, right? All these things were actually before before J.J. Thomson. There were all these guys, Tesla, this Franklin, right? So all these guys had a concept of electricity, right? You will actually, when you go to 12th class, right, you will actually understand there is a thing called as electrostatics. Okay, so electrostatics means even though I don't know that this is electron, I didn't give the name it as electron, but still there was something flowing. Like that's what you have to understand. But again, we don't have to go into the details. That's actually a good question. You can actually go look into the history. What concept, right, they had for explaining how a battery works and all at that time. You can actually look into it. It actually will be funny if you look into it. Now we have a very proper picture, obviously, and this might also change in another 100 years. Who knows, right? Okay, fine. So what I was telling is,
okay, sir.
Yeah, cool. So we have perforated anode and there is a coating. Now I'm going to switch on the battery. Okay, I'm going to switch on the battery. Now what J. Thomson observed, right? What J. Thomson observed is that something like some kind of wave or some kind of something was moving from the cathode and it was moving towards the anode. Okay, he found out that something was moving from the cathode and it is moving towards the anode. Now, how did he find out? It was not visible to the naked eyes. Okay, this rays or this whatever moving from the cathode to anode, it was not visible to the naked eyes. Okay, so for that purpose only I have this ZNS screen. Okay, so if something comes from here, crosses through these holes which I have, and if it is going to hit this particular screen, right? I mean, I'll take some other color. Okay, if it is going to hit the screen, I am going to have some bright spots formed. Okay, this moving something, right? The something is moving from the cathode to the anode. Now, how do we prove it? Because it is, we don't know whether, because it's not visible to the naked eyes, right? So we have to somehow see, like, somehow we have to see whether something is moving or not. So for that purpose only, I have a ZNS screen here. Okay, so if something is moving from cathode to anode, it is going to cross the anode because it is going to have some holes and it is going to hit this ZNS screen. Once it hits the ZNS screen, right, I am going to have some bright spots, and this bright spots can also be called as scintillations. Okay, SCINTILLATIONS. Okay, scintillations, SCIN. Scintillation basically means bright spots. Okay, now with the help of these bright spots, he confirmed that something is moving. Okay, something is moving from the cathode to the anode. Okay, now this was confirmed. Now next, what you wanted to understand? Okay, something is moving from cathode to anode. The first question you wanted to answer was whether it's charged or whether it's neutral. That means he wanted to check whether this contains any charged particles or nothing. It's just some random substance moving. Okay. Now, second question he wanted to ask is, if it is charged, right? If charged, right? He wants to know whether it is going to be positive or negative. Okay, right? First thing what he wanted to understand is, he wanted to understand whether it's charged or neutral. Right. Second thing is, if it is found charged, he wants to know whether it's a positive charge or negative charge. Okay, right. So for that, what he did, right? What he did is, let me draw a rough diagram again. Okay, so this is the cathode ray tube and this thing. What is that? Electrodes, cathode and anode. Say now the cathode rays are moving like this. Okay, now what he did is he supplied or he put one more set of electrodes. Okay, I have to draw that. He put one more set of electrodes. Okay, he put one more set of electrodes. In a sense, nothing. Another battery is connected. Nothing else. Okay. Now, what he understood is, if this, just give me a moment. Right. So what I was trying to say is, if this extra electrodes were not there, okay, if this extra electrodes were not there, cathode rays moved in straight lines. Okay, and what I'm telling is, if this extra electrodes are not there, if this is not connected, right, the cathode rays moved in straight lines. That's what he observed, right? But if this is present, that is, if the electrodes are present, right, what he understood is, they are not going to move in straight line. They are getting deflected like this. They are not moving in straight line, but their path is changed. Okay, their path is changed. It is not a straight line. It is getting deflected. Okay, now it's very simple to understand that I supply some electric field, right? This is some electric field supplied. If the electric field is not there, it is moving in straight line, right? But if the electric field is applied, it is getting deflected, right? Now, what do you mean by this? Obviously, I can conclude that cathode rays are going to be charged particles. Okay, I'm sorry, like if you're wondering what are these cathode rays, there's something which is moving from the cathode to the anode. Right, that is what is called as cathode rays. Cathode rays. Now, why it's called cathode rays? Because it is originating from the cathode. Very simple. It is starting from cathode, moving towards anode. Though that is why it's called cathode rays. Okay. So again, I repeat, people. J. Thomson put extra electrodes. Okay. Now, when these extra electrodes were not there, the cathode rays moved in straight lines. Right. But when this is connected, when the extra electrodes are connected, they got deflected. That means, obviously, that they are charged particles. Okay. Now, once decided that they are charged particle, deciding whether they are positive or negative is very easy. Right? Why? Because you see, this is positive, right? Anode is positive and cathode is negative. Right? And what I'm seeing is that the cathode rays are moving towards the positive electrode. Right? It is moving towards the positive electrode. Now, also on one more thing, also you can see the extra electrodes you conducted here. This is an extra electrode, right? Now you see this is the positive terminal. Okay, this is the positive terminal. The deflection is happening in the direction where I have the positive electrode. Again, I repeat. Okay, the deflection. If I connect the extra electrode, deflection is happening, no straight line. Right. Now, if you see how the deflection is happening, okay, you will understand that it is moving towards. It is deflecting towards the positive electrode. Okay, and second thing is that the original cathode rays are moving from cathode, which is negatively charged, to anode, which is positively charged. Right. Now, can I conclude, if something is getting attracted towards or something is moving towards a positive charge, so definitely it should be a negative charge. Hope
Sir?
Yeah, please tell me.
Sir, why did he put zinc sulfide only behind the anode? Why didn't he try putting it behind the cathode too?
Coming to that, well, actually a good question. If he would have tried, right? If you would have put a if you would have put this perforated cathode and put a certain screen here, eventually you would have observed some scintillations here also, no doubt about it. Okay, we'll
It's
come to
done
that.
later, right?
Yeah, it will come later. There's this guy called as Goldstein, right? He was the one who founded protons. Exactly same thing, everything done, but instead of using perforated anode, he used perforated cathode and the ZNS screen on this side, ZNS coating on this side. Then he founded protons. Anyways, we'll come to that. Okay, right, fine. So now we understood that they are charged, that is the cathode rays are charged, and they are negatively charged by conducting the experiment we found out. Okay, fine. So 2 questions were answered. One, whether it's charged or uncharged, and if it is charged, whether it's positive or negative, we understood it is charged and it is negatively charged. Very simple. Okay, right. Now, next thing what you wanted to know, the third question you wanted to answer is, right, third question you wanted to answer is whether these cathode rays are particles or are they waves? Okay, whether they are particles, like for particles means we are particles, right? We are made of one substance. Waves, you know, gamma waves, X-rays, all these are waves, right? So this can be anything, right? Like this cathode rays, like it can be charged, okay, it can be negatively charged, okay, but this can still be a particle or it can be a wave, right? Particle means it will be moving like this, normal straight line. If it is a wave, it has to move like this and all. How will we know? Right? So he wanted to answer this question, whether the cathode rays, okay, I understand that they're negatively charged, but whether they are negatively charged particles or whether they are negatively charged waves, he wanted to understand. Okay, right. So for that, what he did, let me see. Right. So again, I'm going to take the cathode ray tube to electrode. There is cathode and anode. The cathode rays are coming. Okay. Now what he did is, he did this. He put a rotor here. Okay, bear with my diagram, people. Right. So if something hits here, it is going to rotate. It's like a turbine. Okay. If something hits, if you give some force here, it is going to rotate like this. Okay. Right. Fine. Now, what he understood, like when he did this experiment, what he found out was that he found out that this paddle wheel, we can call it as a paddle wheel, right? Paddle wheel is rotating. Okay, this paddle wheel was rotating. Okay, now very simple experiment. Okay, I had the cathode ray. In the path of the cathode ray, I put a paddle wheel and I found out that the paddle wheel is rotating. Okay, fine. So what can we conclude from this is the question. Okay, guys, right. Now, please understand, if this has to rotate, okay, if this paddle wheel has to rotate, whatever is hitting it, right, the cathode rays are hitting it, obviously that is why it is rotating, right? So whatever is hitting it, that is the cathode rays hitting it, should have some energy, or else it's not possible, correct? The cathode rays, if I find that the paddle wheels are rotating because the cathode rays are hitting this, obviously this cathode rays should have some energy. Okay, and according to people that time, okay, according to basically Einstein was a very big shot here. Okay, Einstein at this particular point of time in history, Einstein was a very big don in science. Okay, so I hope you know is this thing. What is that?
E is equal to mc square.
Yeah, A is equal to mc square, famous equation. Okay, so what I understand from this equation, forget about this C. Okay, what I understand from this equation is that if something needs to have some energy, it needs to have some mass. Yes, obviously it will have some velocity because it will be moving. That is okay. But what I understand is, if something is going to have some energy, anything which has some energy should have some mass associated with it. Right now, can I answer me this question? Can I tell from the signal towers? Okay, we had the phone signal towers, right? I am saying that I have 10 kgs of X-rays coming every day. Okay, again, look at the statement. I'm saying that there is 10 kgs of X-rays coming from the signal tower every day. Does it make sense? Obviously not, right? If something is a wave, we generally don't speak about the mass of the wave because they are massless. Remember, waves are massless. X-rays, gamma rays, all of them, whatever we have, whatever types of rays you have, right? All these waves are massless. Okay, so if something has energy, right, and it has to have some mass, and which will have mass? Only particles will have mass. Waves will not have mass. Okay. Yeah. Any
Sir,
questions? Yeah, please.
sir, like, does the zinc sulfide glow
Okay.
when they are hit by waves?
Correct. I told you, glow means the bright spots. I told you, right? Scintillation spots. That will happen. Yeah. Yes, it's okay.
Anish, mute.
Sir,
Yeah. Yeah, I think you have to mute yourself, Pranav, whomever it is. Okay. Yes, please tell me. Someone has asked something. Yeah.
sir, could you repeat, sir? I actually couldn't hear.
Yeah. So what I was telling is, it is it is not going to give you any fluorescence, but it will give you bright spots. Right? There will be some gray color spots which will be formed on the screen. The ZNS will be black in color. Right? On the black color coating, you will see some gray spots. That's what will happen.
So this is when radiation hits.
Yeah, correct. This is when the cathode ray hits the ZNS screen. Yes.
Sir, then if there is H2 gas present, then anyways it will glow, right?
Not necessarily, right? H2 gas, yeah, if I apply so much of electricity, okay, there is, I told you that it's a very high power supply and all, so the H2 gas can be converted into something else, right? Something else in the sense it can be converted into its isotopes, right? And these isotopes are radioactive. Like, see, please understand, I have hydrogen, deuterium and tritium, right? This hydrogen is not radioactive, but deuterium and tritium are radioactive. So because of that, you might see some radioactivity. You might see. Because I have high power supply and this hydrogen can be converted into deuterium or tritium and they are radioactive. Possible. Yeah.
Sir, no, what I was asking was without supplying electricity, if there is hydrogen gas present inside the tube, then won't the zinc sulfide glow?
No. Hydrogen gas is a neutral substance, right? It doesn't have any energy as such. It is energy as such. Like, I need to have something which is going to be, or the ZNS screen's property is such that it is going to, it is going to give scintillations only for, some kind of waves or some kind of charged particles. Those kind of things only will give scintillations. Normal gas will not give scintillations. That's what I'm telling.
Okay, sir.
Okay, right, cool. So we understood that cathode rays are particles now because the paddle wheels are moving, right? And if something paddle wheel has to move because these are hitting it, right? They need to have some energy, and according to Einstein's equation, anything which has energy should have some mass. Obviously, waves cannot be. Waves are massless, so only particles are having mass. So we understood, or now we understood certain things about cathode rays, that they are negatively charged particles.
Sir, but then this was proved wrong, right? Afterwards.
Obviously, they have both dual nature. We'll come to that. Yes.
Yeah. Okay.
Yeah. Right. Okay. So we found out that the cathode rays are made up of negatively charged particles, right? And this negatively charged particle, J.J. Thomson called them as electrons. That's it. Right. So this is how, right? This is how electrons came into the picture. The discovery of electrons came like this one. Okay. So with the series of experiment, right? He first found out that it's charged, then he found out it's negatively charged, and then on the third experiment, he found out that they are made up of particles and not waves. So eventually, it is now going, the cathode rays are made up of negatively charged particles, and J. Thomson gave the name electrons. Very simple. Right? Okay. Now he conducted still more, 2-3 more experiments. Okay, like we understood that they are made up of negatively charged particles called electrons. Now he wanted to know, since they are charged, that is, since they have some charge and also has some mass, right? It has both charge as well as mass because they are particles, right? So J.J. Thomson wanted to find this ratio, E by M ratio. E is charge, right? And M is the mass. Okay, now we don't have to go into the details, right? Because it's not important to you. Because even though I get into saying you that this is the experiment and this is how the calculations are done. Excuse me. Sorry. Yeah. So even though I'll tell you what kind of experiment he conducted and then how this E by M ratio was found out, you still don't have enough physics. You'll study whatever physics we need for us to understand this. You will be studying them only in 12th class. Okay, so we will not go into the details, right? But in your book, they would have given you this charged E by M ratio. Okay, and I think in your book they would have even given what kind of experiment they did, but I think it's not going to be, it is not involved in the syllabus for you. Okay, so all you need to understand is the E by, he did some experiments, okay, and he calculated this E by M ratio, and you have to know the E by M ratio value, whatever value. I'm not good with numbers, so you can check into your book and get to know what is this value, E by M ratio value of electrons. Obviously, this is for electrons. Protons will have some other value, right? Okay, right. This is for electrons. Done. So that is all about J.J. Thomson's experiment, and he found out electrons. I should not say he found out electrons. He discovered electrons. Okay. I hope there are no questions. I think everybody is clear. Whatever we saw till now. Okay. What is the time? Okay. Cool. So yeah, now he found out that there are electrons, right? Now he wanted to give his own atomic model. Obviously, now he created a revolution, right? See, he was actually awarded the Nobel Prize, right? Your J.J. Thomson was awarded the Nobel Prize in physics, not in chemistry, right? He was awarded the Nobel Prize in physics in 1800s. I don't know the exact year, in 1800s. Okay, it was for discovery of electrons, right? But his work does not end here. Okay, now he continued his work, okay, and he gave his own atomic model. Why will he not give is the question, obviously, right? Because he created a revolution. Till say 200 years before that, right? I would say at least 100 years before that, right? Whatever Dalton said was thought to be true. He said that atoms are indivisible and all that, right? So now when he found out that electrons are there, right? The hydrogen gas is going to inside hydrogen atom, right? Inside the obviously include hydrogen gas only, right? So inside hydrogen atom, there are going to be still more these negatively charged particles called electrons. So obviously he wanted to give his own atomic model. Okay, right? So he said that this is how the atom looks and all that. Okay, now what he said is, right? So I hope you all remember there's something called as plum pudding model or watermelon model. All these things that are studied in your lower classes, right? Okay. Now, what you have to understand is, people, even though he found out that there is some negatively charged particle present inside the atom, that is electrons are present inside the atom, still the overall, the atom is neutral, right? Overall, the atom is neutral. That means what? Obviously, I should have same amount of positive charge and the same amount of negative charge. Only then the overall, the atom will be neutral, right? So what he said is that atoms is a sphere, and it's not a normal sphere, it's a sphere of positive charge. Okay, he said that atoms are spheres of positive charges. Okay, and he said the electrons are embedded in the sphere. Very simple. Okay, atoms are, the entire atom is a sphere of positive charge, and inside the sphere, right, these electrons are embedded. Very simple, you can understand. Like I am going to have the sphere, and this sphere is full of positive charge. Okay, and then electrons are going to be there and there and there and there. There is no perfect location at all. He just said that electrons are embedded. Okay, right, fine. Now obviously this is not going to be correct, right? Because if this is going to be an entirely positive charge, right, and I should have very high number of electrons, okay, that is one thing, right? And in another 10 years, in another 10 to, I mean, even say 7 to 8 years after this discovery, protons, nucleus, all these things were discovered. Okay, now when these were discovered into his model, into this plum pudding model, these protons or neutrons were not able to, they were not able to fit inside this. How will they fit inside? Right? And second thing is, he didn't say anything about the position of electrons. Right? Electrons, he said the electrons are embedded, but he didn't say anything about the position of electrons. Okay? Right? So these were all the problems we face with your J.A. Thomson atomic model, plum pudding model. Okay, now these things you have studied in your lower classes, very simple, but more important thing is about the cathode ray experiment and how electrons are discovered. That is what is more important. Okay, right, fine. Now next we'll move on. We'll move on to see how protons were discovered. Okay, I also told you it is going to be very similar to the J.A. Thomson experiment, right? There are going to be little modifications. That's it. Okay, fine. So this protons were discovered by a scientist called as Goldstein. Okay, now same thing he did, right? Right, so he did the same, right? Same thing. Okay, so again, this is negative, that is cathode, this is anode. Okay, now the only difference, as I told you, is that he used perforated cathode, right? He used perforated cathode. That means the cathode which is having some holes. And also the same thing as he did in the previous, what J.A. Thomson did the previous time, he had a ZNS screen on this side, on the left-hand side. That's the cathode side. Okay, so again, he switched on the battery, right? Now he found out that there is something moving from the anode to the cathode, right? So there is something moving from anode, right? Something moving from the anode towards the cathode, right? So he called them as anode rays because they are starting from anode and moving towards cathode, right? Or also they also call them as canal rays. Okay, he also called them as canal rays. Everything, whatever J.A. Thomson did to prove that this is positively charged, negatively charged, whatever he did the same thing, right? He did the same thing. Okay, now only one difference is there. Okay, now what is the difference is in the last time, right? I told you that in the case of J.A. Thomson's experiment, I told you that it can either be hydrogen gas or helium gas. Okay, hydrogen gas or helium gas. Okay, now whatever I used, whether I used helium gas or hydrogen gas, the E by M ratio which I'm talking about, right? The E by M ratio, I told you that he did something to find the E by M ratios. The E by M ratios were same for both hydrogen and helium, irrespective of whatever gas used, right? The E by M ratios were constant. Okay, but here in Goldstein's experiment, right? In Goldstein's experiment, what happened is, if I used hydrogen, there is one value. If I use helium, there is another value. Okay, if I use hydrogen, there is one value, that is E by M ratio was different for hydrogen, was different for helium. Right? Now we'll try to understand why this is happening. Okay. Now, how do you think electrons would have come out in the previous case when in the cathode ray experiment, in your J.A. Thomson's experiment, right? What would have happened? Hydrogen would have actually formed 2H plus 2 electrons. Is it not?
Yes, sir.
Right? They would have actually formed this hydrogen because of the passage of electricity, right? You pass electricity here, right? So because of the passage of electricity, H2 would have gotten converted to H plus ions and 2 electrons would have come out. Okay, and these 2 electrons are what is responsible for the cathode rays. Obviously, we know that. Okay, now same thing will happen here. I give the power supply, but I am not interested in this electron now. I am actually interested in the H plus ions. Okay, now please understand, people, H plus, if you just look into it, hydrogen has 1 electron, 1 proton. Correct? We know this, right? Hydrogen has atomic number of 1. That means it has one electron and one proton. So if I convert this into H plus, this electron is gone, right? So what is remaining? There is only one proton remaining. Okay, right? No issues. So now, when this hydrogen was used, when hydrogen gas was used, H plus ions were produced, and H plus ions are nothing but protons, right? H plus ions are nothing but protons. Okay, but when I'm going to use helium, now look at this. Helium is going to have atomic number of 2. That means it has 2 electrons and 2 protons, right? Say now, because of the electricity passed, say helium gets converted to helium plus, assuming. Okay, now what will happen? Helium plus will contain 1 electron and it will contain 2 protons, right? So helium plus, the positive charge is not 1 proton as in the case of H plus. It is 2 protons. Okay, so obviously that is the reason why the E by M ratios were different when I use hydrogen, or when I use helium, the values were different. It's about positive charge. You can see both of them are positively charged, no doubt about it, right? But H plus is a pure proton, 1 proton is there, right? But helium, right, you see it is going to contain 2 protons. So obviously the way in which they move, the E by M ratios, the mass ratios, everything will be different if I'm going to use different gas. But in the cathode ray experiment, what is responsible? Only the electron is responsible, right? So in both the cases, I'm going to have 2 electrons coming out, and that is what is responsible for the cathode rays, right? But in case of the positive charges, H plus and He plus are 2 different species. But electrons and electrons are same. Okay, so that is the only difference between J. Thomson's experiment and Goldstein experiment, or say cathode rays and anode rays. That is the only difference. Other than that, all the things are very similar, exactly same. Okay, they move in straight lines. If I'm going to have some extra electric field supply, they will deflect, but this time they will deflect towards negative electrode because they are positively charged, right? So all these things can be calculated. All these things are very similar to the previous case. Okay, so this is how protons were discovered. Very simple, by Goldstein. Okay, now moving on.
Sir, can you rewrite the equation, sir? I didn't understand that part.
Which equation?
Like how protons.
Oh, okay. This is very simple. I have H2 becoming 2H plus 2 electrons, and helium will give helium plus electron. That's it. That's what we have. Is this
So
what you're
what-
asking?
No, sir. Why is like the proton upon mass ratio differing?
Okay. So why is it differing? Obviously, right? Hydrogen will have 1 mass, even though the charge is same. Assuming the charge is same, it is plus 1.6 into 10 to the power minus 19 coulomb. Charge is same for both of them, assuming, right? But the mass will be different, right? Because it is hydrogen and this is helium. Are you able to understand? The mass will be different. This part, E by M ratios will be
okay, sir,
different
okay.
because
Got
the
it.
mass will be different.
Yes, sir.
Okay, right, cool. Okay. So what I was telling, yeah, the protons part is done, right? The next thing what I have to understand, again, this is not in your syllabus, but is this there in your syllabus, guys? Millikan's oil
Sir,
drop.
it was not given so detailedly.
Okay.
Yes,
But
sir. It's there, sir.
It's there.
Okay. Okay, it's there. It's there in your book, right? But I think it will be given in the green box, which is that means it's not gonna be asked
Yes,
for your
sir.
exam. Right, anyways, I'll give you a brief introduction about this. Okay, right, fine. So Millikan's oil drop experiment, what was it used for first, right? What this experiment was used for what? So J. Thomson found out the E by M ratio. Okay, J. Thomson found out the E by M ratio, but Millikan wanted to find what is the exact value of charge of electrons. This is what he wanted to find out. Okay, so now J. Thomson found out the E by M ratio. Millikan wanted to find what is the value of charge. And obviously, if I can find what is the value of E, that is what is charge, right? If I know the entire value and I know this E value also, and the mass value can be easily calculated, right? Again, I repeat, E by M ratio was entirely given by J. Thomson. Okay, that means this entire value I know, right? What Millikan wanted to do is that he wanted to find the value of charge of electron, that is E value he wanted to find. right? So I know the entire value already, E by M ratio. And if I know the E value, obviously I can find the mass of electron also. Okay, so this is what he wanted to do. Okay, so how he did, we'll try to understand. Okay, so he had a very big chamber. Okay, he had a very big chamber. Okay, then what he did is that say there will be something like this. Okay, please bear with it. Okay, so anyways, I'll tell you the overall picture here. So into this, I will put some oil. Okay, into this, I'll put some oil. Okay, and when it comes out of this particular setup, right, it is going to be atomized. Right, I'm going to have atomized oil. Like that means obviously it'll be like a spray. If I go for any perfume you use, right? If I press it, how small particle comes, right? Say that way you can imagine this. Okay, so the oil will be put inside. Okay, and obviously these are going to be in the form of very atomized, very small particle, oil particles. Okay, right. Now next thing is obviously if I'm not going to do anything, they will eventually fall down, right? Because due to gravity, right? Due to gravity, they will eventually fall down. Okay, so what I'm going to do is I am going to fill this entire thing, right? Entire chamber with X-rays. Okay, I'm going to fill this entire chamber with X-rays. Okay, right. Now what will happen if I'm going to have X-rays? Now please understand, X-rays will ionize the oil particles. Right? What do you mean by ionizing? It will be easy. Basically, when it comes out of the setup, it will be atomized oil. Right? Now this atomized oil will be neutral when it comes out. Right? But the moment I'm going to pass X-rays onto this atomized oil particles, they will become ionized. They'll either become positively charged or negatively charged. Is it not? But he found out that they're going to become negatively charged. Again, the way he conducted the experiment, certain things were not clear, right? So all you have to understand is X-rays ionized the oil particles. That's what you have to understand. Okay, and the strength of the X-rays, right? The strength of the X-rays, how much X-ray you are going to give, right? It is going to be in such a way that this all oil particles are suspended. What do you mean by suspended? They are not going to reach the ground. They are going to be there in the middle level itself. They're going to be hanging. I would say that's the correct word if I have to use. They should be hanging, right? Okay. Or if I have to tell you a little more technically, right? Now please understand, there are going to be two forces acting here. Two forces acting on the oil particle. One is gravity, obviously. Okay, one is gravity. Now, if at all I need this particular oil particle to stay here only, I don't want it to come down. What has to happen? Obviously, there should be some force which should be pulling it up. There should be some force which should be pulling it up in the like same exact magnitude, but different direction. Right? Only then it will stay here. Right? So now that is going to be, so I would say the two forces. One is the okay, first is, I would say, the one of the forces is the gravitational force, right? And this gravitational force has to be equal to some other force, right? So that these oil particles are going to be suspended. No issues. Okay. And for that only I use the X-rays. Okay. Now these X-rays are going to ionize the, oil particles. Okay. So the force is going to counterbalance the gravitational force is the electrostatic force. Okay. The gravitational force and the electrostatic force are going to become equal so that these oil particles are going to get suspended. They're not going to come down. They're not going to move up. They are just going to stay wherever they are. Okay, now I don't know whether you know the equations, guys. Gravitational force Fg is G m1 m2 by r squared. That is the formula. G is the universal gas constant. M1 and m2 are the masses, right? And the electrostatic force is equal to 1 by 4 pi epsilon naught into Q1 into Q2 divided by r squared. Anyways, you don't have to know the details. Okay, you will anyway study them in gravitational chapter. They have a chapter called as gravitational physics. We'll study about this there. And this particular thing we'll study in 12th class. Okay, electrostatic force we'll study in 12th class. Anyways,
learned
so
this,
what?
sir.
Sorry.
We learned this already, sir. It's there in the physics first chapter.
Oh, great. If you have already learned this, well and good. Why not? Super. Right. So what you have here, this G is a constant. Okay. And this R squared and R squared actually will become cancelled, is it not? If I make them equal, right? If I make these two forces equal, R squared gets cancelled. Okay. Right. Now I have this G is a constant, 1 by 4 pi epsilon is a constant, M1, M2. Now this is Q1, Q2, and M1, M2. All these are going to be basically charge by M ratios, E by M ratios. Right. So from this, he did the calculations and he found out what is the charge of electron. Right. And he found out the charge of electron to be minus 1.6 into 10 to the power minus 19 coulombs. Coulomb is the SI unit of charge, people. SI unit of charge. Okay. So the value with this experiment, like you don't have to go into the details of how we calculate and all. You just don't know the equations. This is gravitational force. This is electrostatic force. Now they have to become equal. So something in the derivation he did so that he found out what is the value of charge of electron. That is minus 1.6 into 10 to the power minus 19 coulombs. Right. And from this, obviously, mass of electron also can be calculated. And if I'm not right, I don't want to tell you a wrong value. Mass of electron is, I think, 1.9 into 10 to the power minus 31 kgs. I'm not sure, guys. Please check it. Okay, this might or might not be wrong, but this value is correct.
9.1.
Oh, it's 9.1.
Yes, sir.
Okay, fine, whatever. Right, 9.1 into 10 to the power minus 31 kgs. Anyways, the values are not important. Okay, so you have to understand how this was calculated. That's it. So now we know the charge of electron, mass of electron, E by M ratio, everything we know. Okay, right? Fine. So we understood how electrons were discovered, how protons were discovered, and how the charge value and the mass value of both electron and proton, how they were found out. Everything we understood. Okay, what is the time? Okay, we still have half an hour. Okay, cool. So maybe now we'll move on to discovery of nucleus. Obviously, you're going to see, you know, where we are going. We are going towards Rutherford's model. Okay, Rutherford's atomic model. That's what we are moving into now. Okay, right. So I think this experiment also you would have studied in your lower classes. It's called what? It's called what experiment?
Alpha
Rutherford's
scattering.
alpha scattering experiment. Or other names?
Gold foil experiment.
Gold foil experiment. Right. So we know what are we going to do. We'll just have a quick recap of whatever you studied in your lower classes. Okay, right. So what Rutherford did is he took a very, very thin gold foil. Right, he took a very thin gold foil. Okay, now what he did is to this thin gold foils, he made alpha rays bombard or alpha ray. He made alpha rays to hit this thin gold foil. Okay, and one more thing also he had a ZNS screen. This is a ZNS screen behind the gold foil. Okay, right. Actually, he will have somewhere here also, wherever it is, and he had here also the ZNS screen. These are all ZNS screen. This is also a ZNS screen. Okay, I'll tell you why why are all they used. Anyways, right. So first you have to understand what are these alpha rays. Okay, now alpha rays are nothing but He2 plus ions. Okay, alpha rays are nothing but He2 plus ions, doubly charged helium. Right here, doubly charged helium is basically alpha rays are made up of doubly charged helium ions, He2 plus ions. Okay, right, fine. Now what he did is I told you that he made this alpha rays bombard to this gold foil. Okay, now he had 3 observations. Okay, he had 3 observations. First observation is most of the rays just went through the gold foil. Right, most of the rays went through the gold foil. That means obviously they will have scintillations on the ZNS screen. Okay, you will have scintillations here. Right, so most of the thing went through. the gold foil. That was the first observation. Second observation is some of the rays, they just hit and they got deflected by some angle theta. Okay, some of the alpha rays hit the gold foil and they got deflected in the opposite direction, or in some angle theta, they got deflected. Again, you will see that on the screen here. Again, you will see scintillations, right? So deflected by some theta, by some angle. Okay, that's the second observation he made. Right now, third observation. Okay, third observation, what he made is very rarely, very rarely, only 1 in 1,000 rays. If I had 1,000 rays, I'm sorry, if I had 1,000 rays, 1 in 1,000 rays hit the gold foil and it retraced the path. I mean, I'm not drawing it properly. Only one line should be there, right? It just hit and came back in the same direction. Okay, so what you have to understand here also deflection is happening, right? But the deflected angle, the theta value is 180 degree, right? Whatever the path it took, alpha rays took, after hitting the gold foil, they went back in the same direction, 180 degree deflection. Okay, now these three were the observations he made. Okay, now based on these three observations, he made three conclusions. Excuse me. Excuse me. Right. So he made three conclusions. Okay, now what conclusion he made? Based on the first observation, that is most of the rays just went through the gold foil, he concluded that most of the space inside the atom is just empty, right? He just concluded that, right? Since most of the rays are going through the gold foil, right? He understood that, or he concluded that most of the space inside the gold atom are empty. Most of them are empty spaces. Okay, fine. Second thing, based on the second observation, right? Deflected by some angle theta, right? Now, what you have to understand is, why is there in the first place a deflection, right? Why is there a deflection? Was what you have to understand. Now, see here, alpha rays, I told you that they are made up of positive charges, basically He2 plus ions. Okay, now inside the gold atom, I already know they have electron, they have proton, everything is present. Okay, basically these empty spaces and electrons will go hand in hand. Nothing will happen to the alpha rays. Okay, but if when the alpha ray hits the gold foil and it encountered a proton, which is positively charged, right? If it encounters an electron, no problem. It will just go through or something will happen, right? But if when the He2 plus, when the alpha rays hit the gold foil and it found the proton, obviously there'll be some repulsion, right? So because of the repulsion only, there is some deflection happening. Deflection at some angle of theta happening. It hits and it gets repelled and it comes back like that. Okay, so now this deflection, right? This deflection can be attributed to the presence of protons. Very simple, because I'm going to have repulsion.
Sir, so alpha particles are negative in charge?
No. Alpha particles are positively charged, He2 plus ions, right? So He2 plus positive, protons are also positive. So what will happen? Repulsion will happen.
Oh, okay.
So once it hits and it repels back, deflection will happen. Okay, right. Now, third observation, that is, he found that 1 in 1,000 rays, right? Very rarely 1 in 1,000 rays deflected by an angle of 180 degree. Okay. Now, what we have to understand is, if there is only one type of positive charge, that is only protons are present. Okay. Now then all the cathode rays should go at the same kind of angle theta, whatever be the angle, right? But if I'm going to have 180 degree deflection, right? Whatever the path the alpha ray took, it is going to go back in the same path. That means obviously it is not a proton. If it was a proton, normally this would have happened, right? The normal deflection would have happened, right? So if I need to have a 180 degree deflection, people, I need to have a very strong positive charge. Is it not? Only that strong positive charge is capable of deflecting the alpha ray in 180 degree deflection. Yes, some question is there?
Yes, sir.
Yeah, tell me.
Sir, how did he like find out that they got deflected by 180 degrees?
Yeah, exactly. I told you that he had ZNS screen here also, right? There also. So once it hits, it came like this, scintillations. Yes, understood?
Okay, sir. Yes, sir.
Right. Okay. Right. So now if I'm going to have 180-degree deflection, right, there should be some very strong positive charge. Obviously, if it was proton, normally this would have happened, right? Normal theta would have happened, right? Now, this strong presence of positive charge, right? Only that is capable of giving him his 180-degree deflection. He called that particular very strong positive charge as nucleus. Very simple. Okay, so this is how, by based on the third observation only, he discovered nucleus. No issues. Okay, now he found out that there are electrons also. He accounted for electrons also, protons also, and he discovered nucleus also. And I told you that this guy Rutherford is a student of J.A. Thomson. Okay, so it's like the student, disproved the teacher's theory. It's like that. Anyways, so now he discovered nucleus. Again, he wanted to give his own model, right? How the atom looks, he wanted to tell, right? So this is what he said: Rutherford's model of an atom. Okay, so what he said is the nucleus will be at the center, right? I would say nucleus plus protons will be at the center, and the electrons will be revolving around the nucleus. That's it. That's what he said, right? Nucleus and the protons together will be there at the center, right? And electrons will be revolving around the nucleus and protons. So this is what he said. So I'm going to have a big chunk of positive charge, that is nucleus plus the protons, okay? And he said the electrons are continuously revolving around the nucleus. These are electrons here, right? This is nucleus here. Okay, this is what is your Rutherford's model. It's also called as what? Planetary model, right? Why? Because this is like the sun, and the electrons are like the planets which revolve around the sun. It's like that, right? So it is also called as planetary model. Okay, right. Now again, this had its own problems. Okay, what is the time, guys? Oh, we still have time. Right. So now this had its own problems. Right. The first problem we already know is the stability. Right. What stability? Now I know it's very logical, right? If I am going to do a lot of work, say assume that I have to go around playground for 10 times. I have to run. Right. Obviously, after one round, second round, third round, it is going to become more and more difficult, right? Because I'll be keeping on losing energy. Right. Now, same thing will only happen for electrons also. Right. Now, they have to move around the nucleus. That is one thing. And they have to move around the nucleus, overcoming the attractive force. Please understand, these electrons are negatively charged. Nucleus is positively charged. Already the nucleus will be attracting electrons into it. Right. And in spite of the electron has to revolve also. Right. So first thing is it has to move. For that itself energy will be spent, and it has to move against the force of attraction from the nucleus. Right. So a lot of energy will be spent. Right. So at a point of time, what will happen? Right. At a point of time, the electron will lose all its energy and will eventually fall into the nucleus. Right. The electron will lose all its energy. Right. And it will fall into the nucleus. Okay, that means what? Electron itself will not be there. If electron itself will not be there, obviously stability of the atom is a question. Right? The stability, obviously electrons are not there. That means that the balance, the neutral being, that is the amount of positive charge should be equal to the amount of negative charge. For the overall atom to be neutral, all these things will become a problem. Okay.
Sir?
Yeah, tell me.
Sir, then why isn't Earth colliding with?
Yeah, coming to that, we'll have something called as orbits, right? In that particular orbit, if they're going to stay, right, they will not lose any energy. It's like that. That's a special orbit. You'll come to that. When I go to Bohr's model, after this, we'll go to Bohr's model. Actually, at that time, you will be unable to understand how this problem of stability was overcome when I go to Bohr's model. Right? Why? Because he didn't talk anything about the electron's position. He just said the electrons are revolving around the nucleus. Okay. But if I'm going to have a separate home or separate place where the electron will be present, right? And if it is going to be there at that particular place, right, it is not going to lose any energy. It's a special kind of place, something like that. We'll speak more about it when I go to Bohr's model, right? When you understand Bohr's model, again, you're on the question of how planets, does the same thing as in the case of electron, you'll understand how it's all connected only. Okay, right? Fine. So now the stability was the question, right? Eventually the electron will fall into the nucleus. Now, second thing is there is this thing called as spectrum, people. Very important term. Okay. Now, please understand spectrum. When I tell spectrum is nothing but collection of energies. Right? Now, see, when I tell electromagnetic spectrum, right? When I tell electromagnetic spectrum, that means what? Nothing, it is just a scale. Okay, it is just a scale which is going to include the values. Say it can either be in terms of wavelength. Okay, I'm going into some details, guys. I hope you all know this term called as wavelength. Everybody knows?
Yes, sir.
Right. So I'm talking about the lambda values, wavelength value. Even though you don't understand, don't worry about it. You talk about the energy itself directly. Okay, we can talk about the energy itself directly. Okay, so what I'm telling is, when I say electromagnetic spectrum, it is nothing but a scale like this, right? And this scale is going to have values of energy or wavelength or whatever it is. We can just consider energy for now because we don't know what is exactly how they are connected and all that. Right? These are energy values. Okay. Now there is some process. Okay, there is some process, right? And during that process, some energy is coming out, some electromagnetic radiation is coming out, right? And you want to know what is the electromagnetic radiation. Again, I repeat, there is some process. Okay, during that process, some electromagnetic radiation comes out. Okay, now what you want to know is what is this electromagnetic radiation, whether it's an X-ray or a gamma ray or a microwave or a radio wave. Right? So please understand, there will be so many, right? Before we moving on to this, we'll first try to understand what are all the different electromagnetic waves, electromagnetic radiations, right? Say starting with you have radio waves, microwaves, IR, infrared, right? Then you have the visible, that is our normal light, what we can see, UV, ultraviolet, right? Then you have X-rays, then gamma rays, right? So these are all the different types of electromagnetic radiation present. Okay, and all of them will have different energy value. Okay, I would say gamma rays will have the highest energy and radio waves will have the least energy. Okay, this is lowest and this is the highest. That is, gamma rays are the highest. Okay, so this scale will be in such a way that you start with, say, lowest energy and you go to the highest energy. That is how the scale will look. Okay, right? So I told you there is some process, right? And you want to, then during the process there is some electromagnetic radiation coming out. Okay, and you want to know what is electromagnetic radiation. At that time you will go for this. It's called spectrometer. Right? Now this spectrometer, like say you just keep the spectrometer in the place where the radiation is coming from, right? Say it's coming from your hall, you keep it in the hall, right? So what will happen is it is going to show some reading like this, right? It is going to show some reading. Say it says that IR rays are coming out, something like that.
Sir, but then how do we find that from a place electromagnetic radiation is coming out?
Absolutely. Like there are certain sensors for that. Right? Now there are certain sensors which will sense if there is some electromagnetic radiation, it will sense and tell you, okay, there are some electromagnetic radiation. There are electric components present in this sensors. If I have to tell you one example, even if you have a normal magnetic compass, right? You have a magnetic compass, right? The compass needle. That also will deflect if you have any electromagnetic radiation, right? That is the very simplest of them all. You can go for more and more sophisticated instruments, which will tell you, okay, there is the electromagnetic radiation coming out, like that way, right? When you go to your atomic power plants, right, Kudangulam or any other power plant, you go atomic power plants, they will always install the sensors, right? Now, if the level of the electromagnetic radiation goes above certain level, they will switch off the entire plant because it is very harmful for the community, right? So like that, there are some sensors which can be used to detect whether some electromagnetic radiation is coming out or not. Okay. Now, why did I come to this entire electromagnetic spectrum? Why did I, explain you is that time people. Okay. So why did I come here all the way through this electromagnetic spectrum? Is that this spectrum, right? Basically, spectrum is nothing but the data which you're going to get. Say now you see that the data which you got here is like this. Okay. Now this spectrum, what you can get from the spectrometer can be of two types. Okay. One is what is called as line spectrum. The other one is what is called as line spectrum, continuous spectrum. Okay, the other one is what is called as continuous spectrum, line spectrum, continuous spectrum. Okay, now what do you mean by this? Nothing. In the spectrometer, if you're going to get just one line, one single value of energy, right? That if you get, it's called a line spectrum. Okay, but say in the previous case, how you got? You got a range of values, say some 10 to 100. Right? Entire value is now taken. The data gives you like this. That is called a continuous spectrum. Hope you understand. A line spectrum means a single value, one single line in the spectrum, in the spectrometer. If it is continuous spectrum, I'm going to have a range of values, say 10 to 100 or 10 to 20, something like that. This value, say only 10. Okay. Those two are the kind of data which you can get. Okay. Now, when I go to Rutherford's model, people, right? When I go to Rutherford's model and I check the spectrum, right? I check the spectrum because electron is losing energy, right? When it loses energy, obviously some kind of electromagnetic radiation is going to come out, right? Because it will eventually lose all its energy and will eventually fall into the nucleus. Correct. Now, what kind of spectrum can we expect? Can you think and tell me? Whether can we expect a line spectrum or we can expect a continuous spectrum for this case, for the first model, for electron? What can you expect?
Is it continuous?
Yeah, it should be continuous spectrum, right? Say initially I had 100 joules of energy.
The energy will be reducing, sir.
Exactly, right? So initially I had 100 joules of energy for electron. Now this 100 will become 90, 90 will become 80, eventually it will become 0, right? So see how many values are there, right? There are going to be a number, not only single value. From 100, it goes to 0. So many values we can get. Right. So what we expect from Rutherford's model is that I am going to have continuous spectrum.
Sir, could you repeat what continuous and line spectrum?
Sure. Right. So when a spectrum, there are two types. One is called continuous, another is called line. Right. So in the spectrometer, this is the spectrometer, right, which contains all the values. Right. Now, during some process, if you get the data like this, one single line corresponding to one single value of energy, that is called a line spectrum. In continuous spectrum, say the radiation which we get is from 10 joules to 100 joules. All the values are included, right? Now this entire area will be shaded then. That is called a continuous spectrum. Not a single line, but a block of data. That is a continuous spectrum. Yes, understood?
Yes, sir.
Okay, so now we understood that if electron loses energy, say from 100 it becomes 0, there will be a lot of values involved. So obviously what kind of spectrum can we expect is a continuous spectrum. Okay, but what we see in reality, right? What we see in reality is that I am going to have only line spectrum. Okay, this is not happening in reality. Okay, continuous spectrum is what we expect, right? Obviously, but what I'm going to see in reality is that I'm going to get one single value, even though the electron is losing its energy and stuff, right? I'm going to have one single value only. That is a line spectrum only we are going to see. Okay, now how we do that right? How is it that I'm going to get only line spectrum? All those things we'll see in next class. Okay, we still have 10 more minutes. Actually, I'm not that good. I'm not feeling that good. We'll actually stop the class here. Okay, so next class, tomorrow's class, right? We will try to understand why is there a line spectrum, right? Actually, after this, we are going to go to the famous personality, that is your Planck. I told you what Planck did. Planck was the first scientist to disprove Newton, right? So when you understand what Planck said, right, from Planck you can easily go to Bohr, right? So that is what will be our agenda for the next class. Okay, Planck's will take only 20 minutes, but Bohr will take some will take some time. We have to do some problems and stuff, right? So all these things we'll see next class. Any questions anybody has?
So what is the general form to write any symbol for an element, which includes atomic number as well as the charge?
Okay. Say now for hydrogen, for example, chlorine, I want to write. Okay. Now what you have to write is here in this place, you have to write the atomic number. In this place, you have to write the mass number. Say here 1735.5. That's how I write it.
So, but
Okay.
what if we want to include ions?
No, ions we cannot include like this. Like only for elements we can write like this. Ions we just have to write Cl minus. That's it. We will not include any numbers here. Nothing. We will not include anything like that. Okay.
Fine, sir.
Right. Any other questions anybody has? Right. Okay. If that's the case, we'll stop right here and we'll see in tomorrow's class. Right. Thank you so much, people.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yeah.